Okay, I think we'll get started. So today we're going to talk about Newton's second law. If you're coming to us from the G and Lewis project, then I encourage you to go look at the introductory video to this playlist to make sure this is the right series for you. All right, well, Newton's law, we saw F equals ma, and today we're going to take up a important case where there are forces, but the net force is zero. So the vector addition of all the individual forces add up to be zero. So our criteria here is that the net force is zero. And when we have that, we're in a situation of what's called equilibrium. Now, there's two main types of equilibrium, dynamic versus static. Static equilibrium, I guess I have these pictures flip-flopped. Static equilibrium is when the object is sitting at rest and all the forces are equal, so there's no net force, and so it will remain at rest by Newton's first law. And then dynamic is when we're in uniform motion and all net forces are zero, and again by Newton's first law, they will remain in uniform motion. Now this is a little different if you've just had a course in chemistry. We use the term dynamic equilibrium to refer to the chemical equilibrium where the reaction goes forward and a reaction goes backwards. So it's in the beaker, we're still teeming with chemical reactions, but the net effect is that the amount of products and the amount of reactants being made has evened out, and we've reached what we'd call the noticeable end of that reaction where there's no net change in the amount. So that's different. So be careful with that if you're coming from chemistry. All right, well, then once we have an equilibrium, we then can classify it further as to two types. Stable versus unstable. And what we want to think about here is if we introduce a little so-called perturbation. So a perturbation is a minor disturbance to the system. So if my pen is standing like this, I give it a little nudge like that. That's a perturbation. If the system, if you give it a little perturbation and it comes back to the equilibrium, then we call that a stable equilibrium. If we give it a little perturbation and it leaves the equilibrium, then we call that an unstable equilibrium. So imagine an egg sitting on the table. It will sit sideways, and if you give it a little poke, it'll wobble, but then it'll settle back right down to where it was before. But let's say you were very carefully able to balance an egg right on the end, and then you give it just a little tap. Well, it's going to tip over. It's not going to tap and then wobble back to back on top. So this could be sitting, balancing very still, or even my pen here, balancing on the table. Give it a little tap, it's going to tip over. The pen is lying on the table. I give it a little tap, it might wiggle, but it will remain. It'll come back to that same position. So, dynamic, we have motion. That could be stable or unstable. So, for example, a hockey puck sliding on the ice on its edge, it wants to tip flat. That would be unstable. On its flat, how it would normally slide, when it's flat, then give it a little perturbation and it will come back to flat again. So that would be a dynamic unstable, then dynamic stable equilibrium for that hockey puck. Static, we just have a book sitting on the table, or this pen, let's just say this pen sitting on the table. This would be static unstable, and this would be static stable equilibrium. Okay, well, what we want to do now, once we have an equilibrium situation, is utilize this idea that the net force is zero to develop some equations to then do some calculations and figure out the individual forces that are involved. So let's take a very simple example here, just a hanging weight. So we've got some weight, it's attached via a rope to the ceiling. The ceiling is stable there. The weight is hanging. The weight is the object here, and the agents acting on the object are the gravitational pull of the earth and then the rope pulling back up with its tension. The system, the rope will apply as much tension as it needs to counterbalance the weight. So the rope won't just spontaneously pull it up, and as long as the rope doesn't break or stretch, then it won't let it go down. So the tension will just match the upward tension will just match the downward weight force. If we draw a free body diagram for this, here's the weight, here's our free body diagram. We have equal and opposite tension and weights. And just as a reminder, these are not an action-reaction pair because they're on the same free body diagram here, so not an action-reaction pair. Okay, well, whenever we're in equilibrium, we have a net force equation. So we have 0 equals the sum of all the individual forces as vectors, a vector sum. So head to tail adding of the vectors. So in this particular case, we have the tension plus the weight equals 0. And so if we just bring the weight to the other side, we have the tension equals negative weight, or equal but opposite vectors here. We give this a little tap and it will come back to where it was. So this is a stable equilibrium. So we have a static stable equilibrium here. Let's consider another example here. We'll be pulling a box across the floor at a constant velocity. So the box is going to be the object. We're going to be the agent mediated through the rope, so via tension. Gravity will be an agent working on this to pull the box downward. We're going to have a normal force from the floor supporting that box, and then we'll have a frictional force opposing our motion. So when we draw the free body diagram, we have 4 components to force. And because we're at constant velocity, we are undergoing uniform motion, no net force. So the vector sum of our forces, all 4 of them, are equal to 0. We have a dynamic equilibrium because our box is moving. We give this a little perturbation, so we tug on the rope a little bit or loosen the rope a little bit. And then come back to our rate of pull. We end up back to where we were, so we have a stable equilibrium. So we have a dynamic stable equilibrium. Now, this allows us then, in very much the same way we did with this example, to utilize our vector equation component-wise. And that's going to be the key for solving a lot of problems, is to write out the vector equation. Note that we're at 0 because we're in equilibrium, and then that means that the x component and the y component each have to equal 0. Little harder than this one because this only had y component, but this has x and y components. So let's, we're not going to solve with numbers here. We'll do a worked example down here, but let's just write out the components and then write out our equations. So the x components, I'll underline those, are going to be cosine of the total tension and this angle. That'll be pointing in the x direction. The friction is always going to be tangent to a tangent force to the surface here, and it's always opposing motion. So that's going to be negative, and then whatever the magnitude of that friction is. And as of yet, we haven't learned how to calculate friction. We'll do that very soon. So we just know there's a frictional force here. And then the weight force has no x component, nor does the normal force. Those are both in the vertical direction. And I'll put an over bar here on the y component. That's going to be sine of this angle. The frictional force is tangent here, so that's going to be lying, in this case, horizontally. So that has no y component. The weight is negative, the total, so minus mg. And then the normal force is going to be force countering that. Now, notice in the past we talked about like I was standing on the floor and the normal force is pointing up equal enough to balance my weight. Well, now we have two things pulling up, right? We have the y component of the tension and the normal force. So the normal force is not equal to the weight force here. The combined total of these are. And so if we look at this, I'll do over bar here again, the y component, no longer do these cancel. We have this extra term here. And so we end up with an equation involving the tension here. I guess I could have left it like this, but we can rearrange it. And so, of course, we're not putting any numbers in here to solve, but we have an equation now expressed for the y component. Oops, that should be a y component. For the y component. Likewise, for the x component, we're not accelerating or decelerating in the x direction, so the components have to add to 0. So again, if we're trying to isolate the term that has the tension, then we have an equation like this. So the moral of the story is, draw your free body diagram, write your vector equation, should add to 0 if we're in equilibrium, should add to 0. Then you have two equations, and usually in these problems you'll be left with two equations, or with two unknowns. So you'll have two equations, two unknowns. So you'll need the x and the y component to actually solve the full problem. So let's see that in action here. Let's actually do a problem. So let's take a hanging sign problem. So we are a hanging weight problem from two posts, and these posts don't have to be equal. So we can't utilize symmetry here. So we have to fully calculate this whole thing. So let's imagine a post here, solid post here, solid post here, a rope here, and then a 1,000 kilogram weight right there. The setup, it's in equilibrium, nothing is moving now, and if we take a protractor and measure this angle, we get 50 degrees here, and we get 40 degrees here. This is how it would commonly be given to you. Remember now, this is, we measure our angle when we're using our sine and cosine and stuff to get the right SIGN sign of the component. We have to be measuring from the positive x-axis. So this 50 is going to be 50. This 40 is actually going to be 140. And so you have a choice here. You can use 140 as your angle, 180 minus 40, or you can use 40, which is what I tend to like to do, but remember that it's pointing in this direction. Okay. All right. So when we draw the free body diagram, we have tension from the left, tension from the right, and our weight, and those are our three components of force here. So not 4, but 3. So let's try that. We calculate the magnitude of the weight. So 9.8 times 1,000, so 9,800 newtons, and that's pointing in the downward direction. The x direction, the weight has no component to it. So this is only the x component of the tension and the x component of the tension on the left and tension on the right. So the governing equation here for the x is going to be TLX plus TRX equals 0. And so that gives us that these are equal but opposite. And we can see they have to be, because there's nothing the weight can do about it to go this way or that way. The weight only points downward. So the two horizontal components of the tension have to be equal but opposite. So we can write the left as the total tension, cosine of 40, right? We could write cosine of 140, as I mentioned, or cosine of 40 and put the minus sign here. So that's what we're going to do. And then we write the right-hand side as the total tension on the right times the cosine of the 50 there. Okay, the y direction, we have left, right, and now the weight. Now the left and right are pulling together, right? They're both pulling upward, and then our weight is pulling downward. What is our weight? Well, it's the magnitude of this, but in the downward direction, so the negative sign there. Again, we can write these. We don't need a negative sign here because that's going to be pointing, if we use the 40 degrees here, that's going to be pointing in the upward positive direction. So this is fine the way it is. All right, so we've established our two equations. So let's work with them now. So this dash line here, let's start now working with the two equations. So we're going to take this one, set these two equal to each other. So we get TL equals minus TRX. So that's where this minus sign is coming from. And then we have this as our expression. Okay, so this minus sign here is this minus sign there. We can bring this cosine over to the other side, and we can write TL, and we'll cancel out the minus signs. So we'll write TL as a function of TR, and so we have this ratio of cosines. We can bring that to an actual number here, and so we have one equation that the relationship between the magnitudes of the tension is such that the tension on the left is 0.84 times the tension on the right. Okay. All right, now we have this equation right here, but I'm just going to bring this to the other side. So we're going to have the y component of the left, the y component of the right equals to the weight, equal but opposite to the weight. Okay? So in the positive direction. So we can see that here. Now I'm going to substitute in, I'm going to take and get the numerical values for sine 40 and sine 50. And then I'm going to replace this right here. So there's my 84 okay, TRL. There's a TR here. So I'm going to pull that all the way out. So I have distributing this out. Okay. So maybe if you need to pause the video here, substitute this in and then distribute out the right tension. Okay. So this is all just a big number. Right? So we can take and divide this over. And so we have this is this 980 divided by this whole number here, right here, this number. And we end up with 8,056 newtons. Okay, then we plug that back into this equation. So we take it times 0.84 and we end up with 6,700 newtons here. Okay, so these are our two values. So these are the magnitudes of our tension. So we have figured out the actual forces. 8,000 newtons, 6,700 newtons, and 980 newtons added vectorially according to their directions give us the equilibrium condition. So we have utilized the equilibrium condition to find these values. If we were to plug these values back in, then we would get an equilibrium condition. Okay, so that's it for utilizing equilibrium to determine values of each of the forces involved in the total net force being equal to 0.